March 1942, Java, Dutch East Indies. The jungle was quiet again. The bombing had stopped. The smoke that drifted above the palm trees was thin and white, curling into the sky like the last breath of a dying machine. On a patch of scorched earth near the coast, a group of Japanese soldiers stood in silence, staring at the wreck that lay before them. It was unlike anything they had ever seen. The fuselage stretched longer than two fighters end to end. The wings were massive, thick with metal, their edges torn and blackened from anti-aircraft fire. 4 engines sat twisted and silent, their propellers half buried in the mud. The Americans had called it the Flying Fortress. To the men gathered around it, it might as well have been from another world. The aircraft had been part of a U.S. Army Air Force's bombing raid from Australia, one of the first B-17 to strike at Japanese-held territory in the Pacific. Caught by Japanese fighters, it had taken heavy fire, losing 2 engines before turning back over the coast. Witnesses said it flew on stubbornly, trailing smoke until it vanished into the trees. When the patrols found it days later, the jungle had already begun to swallow it. They expected to find a burned-out wreck. Instead, the bomber was mostly intact. The crew was gone, either captured or dead, but the aircraft itself was nearly whole. It wasn't just another prize of war. To the officers who arrived from Batavia, it was an opportunity. The B-17 was loaded onto trucks and brought to a makeshift airfield. From there, engineers from the Imperial Japanese Army Air Technical Research Institute were ordered to inspect it on site. They walked around it slowly, taking notes in silence, their hands tracing the panels, the rivets, the seams. Even damaged, the bomber spoke of something beyond Japan's reach. The skin of the fuselage was thicker than any aircraft they had built. The wiring was neatly bundled, labeled in clear English numbers and colors. Hydraulic systems ran along the wings with redundant connections. The engineers crouched under the wing to examine the landing gear. What they saw was shocking. Hydraulic pistons with triple seals precisely machined and fitted to a tolerance of fractions of a millimeter. The parts could be removed and replaced without modification. Every joint was standardized, every bolt matched. This was not the work of artisans. It was the product of an industrial system. The Japanese engineers were craftsmen, proud of the tradition that their nation's best aircraft, like the Mitsubishi Zero, were hand-built with care and precision. But here was something that looked mass-produced, and yet more exact, more perfect. One officer made a note in his field book: impossible precision by machine, not hand. They had never seen anything like it. That night, the bomber was guarded like a secret. Soldiers built a perimeter and kept locals away. Orders came from Tokyo to secure every piece, every component, and prepare it for shipment. By late March, the dismantling began. Each section of the B-17, wings, fuselage, engines, instruments, was carefully numbered and packed into crates. Engineers tagged the smallest parts: cables, rivets, rubber seals. Even broken fragments of the propeller blades were kept. The operation took weeks. By the time the freighter carrying the crates left for Japan, it was clear that this aircraft would be studied more closely than any other captured weapon of the war. The Japanese expected to find advanced technology. What they didn't expect was the message hidden inside it, one not of design, but of scale. When the crates arrived in Yokohama that summer, they were taken to the Tachikawa Air Technical Research Institute. It was here that Japan's leading aeronautical engineers, from Mitsubishi, Nakajima, and the Army Air Arsenal, gathered to study the prize. The first thing they noticed was how perfectly every part fit into another. The panels aligned with mathematical precision. The wiring harnesses were identical, the clamps uniform, the bolts interchangeable. They compared the bomber's internal structure with their own Ki-21 and G-4M medium bombers. The difference was overwhelming. The B-17's frame was not just stronger, It was engineered for production. Every part could be reproduced by machine. Every joint, every section was standardized. To reproduce such a thing would require not just a factory, but an entire ecosystem. Specialized tools, suppliers, foundries, and training that Japan did not possess. The engineers made sketches, calculations, and metallurgical tests. They measured the alloy composition of the wing spars and discovered a grade of aluminum alloy they couldn't identify. It was stronger and lighter than the type used in Japanese aircraft. They removed a piece of the fuselage to study its rivet pattern. It was uniform to the millimeter, something impossible to achieve with hand riveting. And then came the greatest surprise of all, the internal systems. The fuel tanks were lined with a strange rubberized compound. When punctured, the material swelled, sealing the holes almost instantly. It was a self-sealing fuel system, a design that could prevent catastrophic fires, one of the leading causes of aircraft losses. The radios were equally advanced, long-range, multi-channel, and equipped with direction-finding gear. The oxygen system was integrated into the structure itself, allowing the crew to fly at high altitude for hours. The deeper they went, the clearer the picture became. This was not just a superior aircraft. It was evidence of a nation whose entire industrial strength had been mobilized for precision and repetition. One engineer wrote privately in his report, "We are fighting a war against factories, not against men." In Tokyo, those words would be read with discomfort. The generals wanted tactical analysis, how fast it flew, how high it climbed, how it could be shot down. But what the engineers found was far more unsettling. The real weapon was not the bomber itself. It was the ability to build thousands of them, identical, efficient, unstoppable. And that realization, quietly written in a classified report in the summer of 1942, was the first time Japan's engineers began to understand that they were fighting an enemy they could not catch. Tokyo, July 1942. The wooden crates were unloaded in silence under the watch of armed guards. Each box bore the stenciled word, "captured material." But inside was something far more important than spoils of war. The disassembled remains of a single American B-17 flying fortress. At the Tachikawa Air Technical Research Institute, a small group of senior engineers gathered in a hangar lit by bare bulbs. They worked for Japan's most advanced aviation firms, Nakajima, Mitsubishi, Kawasaki, men who had spent their lives perfecting aircraft built by hand. What they were about to see would quietly shake their confidence in everything they knew. The technicians pried open the first crate and laid the bomber's parts across long tables. The air smelled of oil and metal. A team leader, Captain Sato, read the inventory aloud. Engines, fuselage sections, instrument panels, oxygen systems. Nothing had been left behind. The room filled with murmurs. Some took notes in silence, others simply stared. Even before the first component was reassembled, they understood that this was not an ordinary machine. When they examined the airframe, the surprise deepened. The B-17's internal structure was built like nothing they had ever seen. Perfectly uniform, every rivet spaced to mathematical precision. They pulled out calipers and found each hole aligned within fractions of a millimeter. Every sheet of aluminum was identical in thickness. Every section of the fuselage could be joined to another without adjustment. It was an engineer's dream and a craftsman's nightmare. Japan's aircraft, even the famous Zero, were the product of expert hands. Each plane was slightly different from the next, each fitted and finished by artisans working by feel. But this bomber had been made by machines that didn't make mistakes. A senior metallurgist examined a spar taken from the wing. It was made from an aluminum alloy unknown to them, lighter, harder, resistant to heat. They sent samples to the laboratory for analysis, hoping to identify the formula. Weeks later, the report came back. The composition could not be replicated with Japan's current refining technology. The electrical systems brought another shock. The wiring harnesses were standardized, color-coded, labeled with English numerals. When they tested continuity, they found redundant circuits, a backup system for every critical function. The radio equipment was equally advanced, with components that allowed long-range communication across thousands of kilometers. Nothing about the aircraft had been left to chance. One engineer, educated in the United States years earlier, understood immediately what this meant. "This," he said quietly, "is not built for one plane. It is built for 10,000. They realized the true nature of the threat. The Americans weren't relying on individual genius or heroism. They were relying on a vast, precise system that could create identical machines faster than Japan could repair its own. Over the next months, they recorded every detail. Reports ran hundreds of pages, diagrams showing every valve and gear. The Japanese Air Technical Bureau wanted to know how this bomber could fly home with 2 engines shot out, how it could stay aloft despite hundreds of bullet holes. The answer was simple and devastating: redundancy. Everything vital was doubled or tripled. Even the control cables were arranged in parallel paths, so if one snapped, the others kept the plane flying. It wasn't invincible by design, it was resilient by engineering. They compared the data to Japan's own medium bombers, like the Mitsubishi G-4M. The contrast was painful. The G-4M was fast and light, but fragile, built without armor or self-sealing fuel tanks. A single burst of tracer fire could turn it into a torch. Pilots called it the flying cigarette lighter. The B-17, by contrast, carried armor plate around its crew stations, self-sealing tanks, and multiple hydraulic systems. It was slower, heavier, but it brought its men home. When these findings reached the Imperial Army's upper staff, reactions were mixed. Some officers dismissed the reports as defeatist. Others quietly ordered that Japan attempt to copy what it could. By late 1942, engineers at Nakajima and Tachikawa were assigned a project: reproduce sections of the B-17's design using Japanese materials. They tried building mock-ups of the control systems, the self-sealing tanks, the landing gear assemblies. None met the same standards. The reason was simple: the tools themselves were not precise enough. Japan's factories were small, scattered, and reliant on manual labor. Gauges drifted, drills wandered, and measurements varied from batch to batch. The Americans had machines that calibrated other machines, creating a closed loop of accuracy Japan couldn't match. In their final analysis, the engineers stopped speaking about design and began writing about production. Their strength, one report concluded, is not in the aircraft, but in the method by which it is made. Still, the engineers pressed on. They stripped one of their own bombers to compare materials, weights, and manufacturing methods. Each comparison told the same story. The Flying Fortress was not just superior in parts, it was superior as a system. Some of the team began to keep private notes, realizing that their reports would never change strategy. Japan's military leaders still believed courage and discipline could overcome material disadvantage. But in the drafting rooms and laboratories, the engineers knew the truth. The war had become a contest of industry, not valor. By the end of the year, the B-17 had taught them more than any spy report or captured document ever could. It showed them how far behind they were, not in ideas, but in infrastructure. And for the men who studied it, that knowledge was the beginning of something darker. The understanding that Japan could win battles, but not the war itself. Autumn came to Japan early that year. The skies over Tokyo were gray and heavy with moisture, the air thick with the smell of industry and coal. Inside the laboratories at Tachikawa, the disassembled remains of the American bomber still occupied the central hangar. Engineers moved between tables, notebooks in hand, surrounded by rows of parts that seemed less like fragments of a plane and more like pieces of a puzzle built by another civilization. By September 1942, they had cataloged nearly every component. The team had measured, photographed, and reassembled sections of the B-17 to test their theories. What they learned no longer astonished them, it unsettled them. The deeper they went, the more they realized this aircraft had been designed to remove human error entirely from its creation. Its precision didn't depend on the skill of the worker, but on the accuracy of the machines. And those machines were backed by an industrial ecosystem Japan did not possess. Standardized tooling, large-scale foundries, automatic riveters, and supply chains that stretched from coast to coast. Japan's production system was the opposite. It relied on handcraft, on individual precision. The Zero fighter was a masterpiece of lightweight design and agility, but it was fragile, expensive, and impossible to build quickly. The Americans had chosen a different philosophy: robustness over elegance, durability over perfection. In internal reports sent to the Imperial Army Air Headquarters, engineers warned that the B-17 represented more than a single enemy aircraft. It was a sign of what Japan was truly facing, a nation capable of building hundreds of such machines every month, identical, reliable, and endlessly replaceable. The reports were cautious in tone. They avoided direct criticism of Japan's industry, but carried a sense of quiet alarm. One line, written in careful, formal Japanese, stood out: "The ability to manufacture with uniformity at this scale cannot be met by our present system." But few in command understood the full meaning. To most generals, war was still a contest of willpower, not output. They believed that bravery could overcome machinery. Spirit, they said, would triumph over metal. In the workshops, the men who had seen the inside of the flying fortress knew otherwise. Nakajima engineers attempted to recreate some of the B-17's design principles in test assemblies. They worked on duplicating the self-sealing fuel tanks, mixing layers of rubber and treated fabric, but their materials failed under stress. They experimented with improving the landing gear hydraulics, but lacked the steel alloys required to match the American strength-to-weight ratio. Even the radio systems proved impossible to imitate. Japan's electronic manufacturing base was too limited, its component tolerances inconsistent. When they tested a Japanese-made transmitter against the American set salvaged from the B-17, the difference was humiliating. The American device maintained a clear signal at ranges more than double the Japanese one. By late 1942, engineers began keeping private diaries. These were not technical documents, but reflections. In them, they described the feeling of studying an enemy machine that seemed to belong to another era. "It is as if we are building by candlelight," one wrote, "while they are working under the sun." The truth was spreading quietly among Japan's technical circles. The engineers at Tachikawa began meeting informally after hours, exchanging notes over tea and cigarettes. The talk always returned to the same topic: the realization that Japan's defeat would not come from the battlefield, but from the factory floor. They understood something their superiors refused to see. Even if Japan's best pilots destroyed one American bomber, there would be 10 more behind it, built faster than Japan could train a crew. Still, the research continued. Orders came from the Army to adapt whatever could be learned from the captured bomber into Japan's own designs. At Mitsubishi's plant in Nagoya, new blueprints appeared showing heavier armor around crew compartments and proposals for twin-engine bombers modeled partly on the B-17's internal layout. But these efforts stalled almost immediately. The machinery required to mass-produce such designs didn't exist. Factories lacked precision presses and die sets. Skilled workers were already stretched thin. Each improvement demanded tools Japan didn't have and materials it couldn't import. The captured bomber had become a symbol, an instruction manual written in a language Japan could not read. Meanwhile, on the other side of the Pacific, the United States was entering full wartime production. Factories in Seattle and Wichita produced B-17s around the clock. By the end of 1942, more than 3,000 flying fortresses had been built. American engineers refined designs through assembly line feedback. Japanese engineers, by contrast, were still filing reports by hand. The gulf widened with each passing month. Inside the research institute, the once proud engineers began to speak with restraint. They continued their work with discipline, but the enthusiasm had faded. The project was no longer a pursuit of innovation. It had become an act of documentation. Each test confirmed what they already knew. The Americans were not winning through genius, but through organization. The war had entered a stage Japan was never prepared for. In private correspondence, one of the senior engineers summarized the situation in a single line. The fortress was not an aircraft. It was a mirror. It reflected the difference between two worlds, one where machines served human craftsmanship, and another where human hands served the precision of machines. That difference would determine the fate of nations. Tachikawa, May-June 1943. The morning haze hung low over the Kanto plain as two unfamiliar silhouettes appeared from the south. They were enemy aircraft, but no alarms sounded. Every air defense unit along the route had been warned, do not fire. Fighters rose to meet them anyway, not as hunters, but as escorts. A Nakajima L-2D transport trailed behind like a shepherd. The formation turned toward the hangars. At the Air Technical Research Institute, ground crews lined the taxiway, silent. The captured machines rolled to a stop and the field exhaled. They had come a long way. The first intact airframes were found on Java, where a B-17E lay abandoned at an American maintenance base near Bandung, its nose smashed but its structure largely sound. Others were gathered at Malang and Cirebon, the remnants of hurried withdrawals across Dutch East Indies airstrips. Teams from Tokyo had coaxed at least two fortresses back to health using parts scavenged from multiple wrecks and the reluctant help of captured Allied mechanics. The route home was plotted in segments through Singapore and Formosa, every stop coordinated so that no nervous gunner would mistake them for targets. By late spring of 1943, the prize was on Japanese soil. Tachikawa's hangars filled quickly. One B-17D had already arrived earlier from the Philippines. Now, the pair from Java completed the set. The Institute assigned a formal evaluation team with clear roles. Army engineer Major Kazuyuki Saito directed the work. Test pilots Major Uno and Captain Yagi would fly the trials. A small cadre, Lieutenant Shiyama, Lieutenant Kurusu, Lieutenant Ohara, Assistant Engineer Shimamura, handled structure and systems, while Engineer Kanio focused on the engines. Their instructions were precise. Document everything. The captured technical manuals, seized with the aircraft, meant no guesswork would be necessary. The first weeks were spent on the airframe. Panels came off and went back on. Rivet lines were measured, wing skins weighed, spars examined for heat treatment patterns. It was not simply the strength of the materials that unsettled the team, it was the sameness. A rib removed from one wing matched its counterpart from another aircraft, down to the drilling pattern. Fastener holes aligned without filing. Control surface hinge brackets sat at identical angles across all three bombers. The engineers had spent careers fitting parts to airplanes. Here, airplanes were the fixtures for parts. The conclusion appeared in the notebooks as a dry sentence that carried more weight than any performance figure. Components indicate interchangeability across airframes. Mass standardization achieved. The engines, Wright R-1820 Cyclones, came apart on padded trestles. Gauges and micrometers moved down the tables in quiet procession. Cylinder barrels pistons, connecting rods, crankshafts. Each piece was measured, recorded, compared. The tolerances repeated like a metronome, clearances measured in thousandths of an inch, identical across different engines pulled from different aircraft. Maintenance manuals confirmed what the calipers implied. Field crews were expected to swap cylinders between engines without hand-fitting to treat major components as plug-compatible units. In Japanese practice, a skilled mechanic made a machine work. In American practice, the machine made the mechanic competent. Hydraulics told the same story. Actuators, selector valves, accumulators, and lines were built to common threads and coupling standards. Any assembly could be removed and replaced without rework. Electrical looms revealed machine-crimped terminals, consistent wire gauges, modular black boxes arranged for quick exchange. Even oxygen regulators bore stamps from automobile suppliers, evidence that American industrial capacity extended far beyond the aviation sector and could be redirected on command. The implication was not technical but strategic. An air force backed by an economy large enough to conscript car factories into building precision life support hardware. Outside the hangars, fighter units practiced interceptions against the captured bombers. Ki-43 and Ki-44 pilots flew approach patterns, while cameras rolled for training and propaganda films. The fortresses sometimes repainted with American insignia to simulate combat scenes. Pilots returned with mixed reports. The attack profiles worked on film. In practice, they found the bombers' overlapping guns, 13.50 caliber Browning positions, could cover nearly every approach angle at 600 rounds per minute per gun. And even when a firing pass succeeded, the structure absorbed punishment that would have torn lighter bombers apart. The lesson was not lost on anyone who had escorted fragile G-4Ms across long stretches of ocean. By the end of summer, one of the airframes was lost to accident, a ground collision in a crosswind that sheared a wing and destroyed a parked Ki-49 beside it. The mishap provided an unplanned laboratory. Engineers cut through the damaged wing to inspect inner bays they had not dared open. Hundreds of rivets were sampled. Installation depth varied by less than 1/10,000th of an inch. Diameters deviated by less than 2/100ths. That level of uniformity implied not rows of men with hammers, but automated or semi-automated riveting rigs hammering out patterns dictated by jigs and templates on a production line. The written analyses spread. An Asahi press volume, Anatomy of the Enemy's Aircraft, collated findings on captured Allied types and devoted considerable space to the B-17's structure and systems. Its pages, diagrams, and photographs made the conclusions visible beyond Tachikawa's fences. Designers of Japan's own heavy aircraft offered guarded commentary. Hisanojo Ozawa, whose work touched the Ki-21 and Ki-67, noted that the B-17's lineage reached back to the mid-1930s, yet its iterative improvements had kept it militarily current. Shizu Kikuhara of the Kawanishi H-8K remarked on the cockpit's rationalized controls, subsystems refined to minimize pilot workload. The public tone was analytic, the private recognition was more severe. The Institute's final memoranda on production methods were blunt where they could be. Wing panels appeared to be die-stamped in presses that demanded expensive master tooling. Control surfaces showed identical forming. Main gear struts revealed forging and heat treat cycles best suited to automated machine tools. Drilling jigs had produced repeatable patterns across manufacturers. These were the signatures of an industrial process built for tens of thousands of parts and thousands of airplanes. Japan's dispersed craft-centered factories could produce hundreds, and only with steady inputs of skilled labor and materials that were growing scarce. The numbers, where they could be inferred, were unforgiving. By calculating U.S. serials and production blocks observed in manuals and plates, the team estimated American output trends that were later borne out by wartime totals. Thousands of B-17 from Boeing, Douglas, and Vega by 1945. At peak, dozens per day leaving multiple assembly lines. The precise totals were unknown in 1943, but the slope of the curve was obvious. The enemy was not solving one airplane at a time, it was solving the problem of making many. There were attempts to adapt. Projects to improve turbo superchargers faltered on metallurgy. High-temperature alloys and precision turbine manufacture remained out of reach, making sustained high-altitude performance unreliable. Electrical and radio standardization lagged, component quality varied. Even when principles were understood, the necessary production systems were not. The B-17 could be studied and even flown. It could not be reproduced without the factories that created it. American reconnaissance flights over Japan in 1945 would photograph Tachikawa and mistake one of the evaluation aircraft for a new Japanese heavy type, an intelligence designation assigned to what was, in fact, an American machine under test. The irony suited the story. The bomber had become a kind of mirror, Japanese crews flying in Japanese airspace to learn how to fight American bombers, and learning repeatedly that the most important lessons were not aerodynamic. The men at Tachikawa were not propagandists, they were engineers. Their notes lacked drama, yet between the lines ran a current of recognition that was as decisive as any battle. An aircraft with modular systems, interchangeable parts, redundant circuits, and consistent tolerances said something about the nation that built it. It said that the United States had organized its industry to turn design into volume, error into process control, maintenance into logistics, pilots' survival into a function of engineering margin. On test days, the fortresses lifted from Fosa's runway and circled the plane, their engines steady, their weight obvious but manageable. Ground crews logged temperatures and pressures. Instrumentation teams checked generators and oxygen flow. The machines came back, taxied in, and shut down with a uniformity that matched their construction. What they taught on the ground was sobering. What they implied in the air was final. By the time autumn returned, the evaluation team had what it needed. The reports were complete. Structure, engines, hydraulics, electrics, oxygen, armament, performance, maintenance, philosophy. The recommendation sections were short. Japan could copy certain ideas, but not the system that made them inevitable. That system lived in foundries, presses, gauges, suppliers, and a workforce trained to replace parts, not reshape them. It lived in factories where a single jig could determine the position of 1,000 holes across 1,000 wings, and where a procurement order could summon precise regulators from an automobile plant running a different product the month before. The fortresses would not decide the war alone, but they revealed that the war had already been decided elsewhere.